Hello everyone, my name is SJBIT, working as assistant professor in the department of ECE SJBIT. In last video, we have discussed about FM stereo multiplexing and demultiplexing at the receiver side, and also the demodulator of FM, that is balanced frequency discriminator, or you can also call this as balanced slope detector. So having said that, so we'll continue in today's lecture the phase locked loop PLL. Phase locked loop, it is a indirect method of demodulation of FM signal. The PLL, it is a negative feedback system. The operation of which it is closely linked to the frequency modulation. Where do we use this PLLs? It can be used for synchronization, frequency division or multiplication, frequency modulation, and indirect frequency modulation. So here PLL it is used for indirect frequency demodulation. So consider the diagram of PLL. So it consists of three major components. One is a multiplier. One is a loop filter, and another one is a voltage control oscillator. Voltage control oscillator, it is connected in the form of the feedback loop. From the V of t, it is taken back. So VCO, it is a sinusoidal generator. Its frequency, it is determined by the voltage what is applied to it from an external source. Any frequency modulator may act as a VCO. So it is assumed that initially VCO it is adjusted so that the voltage, control voltage, it is 0. So two conditions here it must be satisfied. One condition is the frequency of the VCO it is set to unmodulated carrier frequency FC. And the second one is the VCO output, it has a 90-degree phase shift with respect to the unmodulated carrier wave. These are the two conditions. The input signal applied to the PLL, it is S of t is equal to AC into sine of 2 pi FCT plus phi 1 of t, where AC is the carrier amplitude. Phi 1 of t, it is given by 2 pi into kf integral between 0 to t m of t into d of t. Phi 1 of t, it is the angle. Kf, it is the frequency sensitivity of the frequency modulator, which is expressed in terms of hertz per volt. Now coming to the VCO, the output at the VCO in the PLL, it is defined as say R of t. R of t is given by AC into cos of 2 pi FCT plus phi 2 of t. So AV, what is it? It is the amplitude. Phi 2 of t, it is the angle, and it is given by 2 pi kV into integral 0 to t V of t into dt. What is kV? kV is the frequency sensitivity of VCO, which is expressed in terms of hertz per volt. The object of the PLL is to generate a VCO output R of t that has the same phase angle as that of the input FM signal S of t. So R of t should be collaborative with the S of t. The time varying phase angle phi 1 of t S of t, it is due to the modulation by a message signal M of t, and it is given by phi 1 of t is equal to 2 pi into kf integral between 0 to t M of t into dt. So here it is required to recover phi 1 of t in order to obtain the M of t. So next we will see the nonlinear model of the PLL. So this is the final diagram of nonlinear model. So let the input to the PLL is it we all know it's a FM wave. S of t is given by AC into sine of 2 pi FCT plus phi 1 of t. So output of VCO, it is R of t. We all just now have given the equations. So when we do the mathematical calculation, we'll land up in an equation wherein V of t, that is the output voltage, is equal to 1 over 2 pi kV into 2 pi k naught into sine phi of t convolution with h of t. So using this equation, we have a series of mathematical step by step solving. After doing that, we'll land up in this equation, which gives us the nonlinear model of the PLL, that is phi 1 of t and phi 2 of t. The difference is taken, that is the error phi of t. Phi of t, it is actually phi 1 of t minus phi 2 of t. The output of the loop filter, it is equal to the convolution of its input E of t and the impulse response H of t. Using that, we will be able to deduce what is V of t. So the multiplier, what we are seeing in this figure, it is now, in the previous figure, it is now replaced with the sinusoidal nonlinearity and VCO. In the previous diagram, it was VCO, now it is replaced with the integrator because of the sinusoidal nonlinearity. So H of t denotes the filter here. Hence this representation, we call this as a non-linearity representation of the PLL. So for the same thing, we are generating a linear model. So here in linear model, what happens is, when the phase error phi of t, this error phi of t, when it is 0, we say that it is in a phase locked state. When phi of t is very small, we can say that sine of phi of t is approximately equal to phi of t itself. So in the previous diagram, whatever was there, few blocks are eliminated here because of the linearity what has been introduced. So here directly 2 pi k naught is multiplied with phi of t, there is no sine term here. H of t, d phi of t into dt, all those terms are literally still existing. So after taking Fourier transforms on both sides and using the open loop transfer function of the PLL, we will be able to deduce the complete nonlinear model into this model, which is absolutely a linear version of the PLL. And in simple words, we can also write in this way. So this is how we will convert a nonlinear to linear model. Due to the time constraints, I am not concentrating mainly on the step-by-step derivations. So using the properties of Fourier transforms, we will do that. In nonlinear effects in FM system, V of t is given by A1 into Vi of t plus A2 into Vi square of t plus A3 into Vi cube of t, like this. So let us consider a communication channel where the transfer characteristics is defined by its nonlinear input-output relationship like this. So what is nonlinearity? It is one form or the another. They are present in all the electrical networks. There are basically two forms of nonlinearity. The nonlinearity is said to be strong when it is introduced intentionally, and you can control it in a specified manner. Say for example, square law modulator, limiters, frequency multipliers, like this. The second version is the nonlinearity is said to be weak when it is when a linear performance is desired, but nonlinearities also arise due to the imperfections. So the effect of such weak nonlinearity, it limits the useful signal levels in a system. So it becomes design consideration. You have to consider it and you have to get rid of it. So after a series of calculations, you will end up in an equation like the output voltage V of t is equal to cos of 2 pi fct plus phi of t into A1 AC plus 3 A3 AC cube by 4. So this is what is the equation which denotes V of t. It is the original FM signal, except the change it is in the only in terms of the amplitude. So thus amplitude nonlinearities of the channel, it does not affect the FM signal as it do in the AM. FM, as it is widely used in the microwaves and satellite communication. The last topic is the super heterodyne receiver. In communication system, it may be AM system or FM system, the receiver not only does the demodulation of the incoming signal, but it also has to perform some other functions. What are the other functions? One is carrier frequency tuning. What do that mean is, it has to select the desired signal, desired radio signal, desired TV station signal, etc. This is the first case. Second one is the filtering. Filtering in the sense it has to separate the desired signal from the modulated signal which are added during the transmission. Filtering has to be done. Third one is the amplification. Amplification means it has to recover the weak signal from the received signal which is almost lost during the transmission. So it has to do carrier frequency tuning, filtering, amplification. So the process of mixing two signals having different frequencies to produce a new frequency, we call that as a heterodyning. Process of mixing two different signals with different frequencies so that you can come up with a new frequency, we call that as heterodyning. The super heterodyne or super heterodyne receiver, it is used to fulfill all the three functions: carrier tuning, filtering and amplification. So it overcomes the difficulty of building a tunable high quality filter, and its application is mainly in the field of analog radio and TV receivers. This is how a simple block diagram of AM receivers looks like. You have an antenna, RF section, mixer, IF section, envelope detector, audio amplifier, loudspeaker, and we have a local oscillator. The receiver of a radio frequency RF section or a mixer, and the local oscillator, an intermediate frequency section, demodulator and a power amplifier is there. The incoming signal, it is picked up by the receiving antenna and it is amplified by the RF section, and it is tuned to the carrier frequency of the input signal. RF section tuning is done. The combination of this mixer and the local oscillator provides the heterodyne function. The mixing happens. Two different frequencies are mixed together to generate a new frequency. Where the input signal, it is converted to a fixed intermediate frequency, IF. Fixed intermediate frequency, which is lower than the input carrier frequency. IF will be always less than the input carrier frequency. So whatever the intermediate frequency is produced, it is the radio frequency incoming minus the local oscillator frequency. LO, it is the frequency of the local oscillator. RF is the input RF signal. IF is the intermediate frequency, because signal is neither it is at the original input frequency nor it is at the final baseband frequency. So this is FIF. The combination of the mixer and the oscillator forms the first detector. Here first detection operation takes place. The demodulator forms the this part. This forms the second detector. The IF, that is intermediate frequency section, it consists of one or more stages of tuned amplification. So it provides most of the amplification and selectivity in the receiver. So the output of the IF, it is given to the demodulator, that is envelope detector, to recover the baseband signal. Suppose if we are using a coherent detector, then coherent signal must be used in the receiver, otherwise whichever is the suitable one. The final operation is the amplification, power amplification of the received signal. So what is the difference between the AM heterodyne receiver and FM heterodyne receiver is, it is the FM demodulator what we use, or you can say frequency discriminator, whatever. In FM, this is a AM receiver. Suppose if you are using for FM system, the message information is transmitted by variations in only the frequency of the carrier signal and amplitude is maintained constant. Rest all concept is same. So any variation in amplitude of the carrier at the receiver, it is due to the noise, or you can say interference. So we'll use the amplitude limiter. Amplitude limiter. If at all, if there is any variations in the amplitude in FM signal, we'll use the amplitude limiter. It is basically used to remove amplitude variations by clipping in the sense removing the modulated wave at IF section output. So the resulting square wave, it is rounded off by a band pass filter. We'll use a band pass filter. It suppresses the harmonics of the carrier wave, so the output what we get, it is a pure sine wave. So what is the difference between AM and FM receiver is RF, mixer, IF section, local oscillator remains the same. The only change what you can see is in this part, that is here you will have a discriminator. Since it is AM, we are using envelope detector. If it is for FM receiver, it will use a discriminator and we will use a band pass filter and then a power amplifier. So this is what is the change we have to note down in a FM receiver. So after this, we have to solve certain problems related to FM modulation and demodulation. Basic problems can be solved using the formulas which we have discussed throughout the video series. So let me summarize what we have learned in the module. First, we started with the basic definition of FM, instantaneous frequency. What do you mean by frequency modulation? What is angle modulation? Basically, in that frequency modulation and phase modulation, two types. In that, first we took frequency modulation. In frequency modulation, based on the beta value, that is the modulation index, you have two types, narrow band FM and wide band FM. So that along with the derivations, the concepts were clearly explained. And after that, we saw certain formulas related to the power, transmission bandwidth, etc. Then we saw the methods of how to generate the FM signal, that is using a tank circuit. You can generate the signals, and then demodulation of FM signal using balanced frequency discriminator, and then stereo multiplexing demultiplexing both phase locked loop PLL. In that PLL, how do we express it in its nonlinear form and its linear form, and what are the effects of nonlinearity in FM system, and lastly we understood what is meant by super heterodyne receiver in case of AM receiver and also in case of FM receiver. So, these are the topics which is explained in module 2. In module 3 we will be taking up the noise concept, types of noises, how do we deduce the equations for different systems AM, DSPSC and FM system, its figure of merits and its variations, which is better and which is not. Like this we will see in the next series of videos. Thank you.